Yeah, please.
Okay, thank you. Shape memory alloys and their functional behavior. So the task of this study was to analyze hysteresis and fast transformations for smart materials reliability. So shape memory alloys possess unique shape memory effect and superplasticity that enable recovery of original shape after unloading without residual strain. The hysteresis loop in stress-strain curves reflects energy dissipation during phase transformations between martensitic and austenitic phases. This nonlinear cyclic behavior is critical in order to design smart materials that maintain functional stability under repeated loading. Understanding these properties enhances reliability and performance in applications demanding precise mechanical response. Uh, Frequency effects challenge traditional SMA models. So, cyclic loading rates impact phase transformation kinetics and modeling accuracy. Cyclic loading frequency influences the kinetics of martensitic or austenitic transformations in SMA, altering their functional behavior. Traditional analytical models often fail to capture the nonlinear hysteresis behavior consistently over varied frequencies and repeated cycles. Limitations in current models reduce the ability to predict SMA durability reliably under realistic engineering conditions, and accurate frequency-dependent modeling is crucial to advance SMA application in adaptive and cyclic load-bearing systems. Harnessing machine learning to model shape memory alloys. So, in these studies, ensemble models were together with explainable AI were utilized to decode complex material behavior. So, uh, we have applied ensemble-based machine learning models that allows to capture nonlinear SMA hysteresis with high predictive accuracy. The nonlinear relationship between stress, strain, and phase transformation is SMA materials were captured successfully. It allows to reduce experimental cost by enabling efficient data-driven simulation of material behavior. And it also enhances scientific trust with explainable AI that identifies key features, influences model prediction. So it also supports model validation, deeper material understanding through transparent AI methods. So in this study, we have employed experimental data of nickel titanium shape memory alloy wire with 1.5 millimeter diameter, 210 length, millimeter length with roughly 56 percentage of nickel and 44 percentage of titanium with impurities below 0.4. Low cycles fatigue tests were conducted at room temperature on STM 100 servo hydraulic testing machine. Test frequency were equal frequencies was equal to 0.5, 1, and 5 hertz, analyzed to cover were varied cyclic loading scenarios. Collected strain and stress data from cycles 100 up to 250 were used to form a data set for machine learning modeling. So was the experimental setup for nickel titanium shape memory stress behavior. And so the goal was to capture strain and stress data under controlled low cycle fatigue at the right frequency. Data preparation split strategy to prevent leakage, data leakage. Grouping data by cycle number ensures training, testing, isolation, and robust model validation. Outcome. So the first was dataset composition. So we move from bottom to top. So it included variable stress, sigma, strain, epsilon, cycle number, n, and loading direction up, down. So it's whether it is going, the curve is going up or down. Second one is group shuffle split application. It splits data by cycle number to prevent data leakage between training and testing sets. Third was training subset selection contained 80% of cycles, ensuring complete cycle exclusive to training data. Point four was testing in subset selection. It contained 20% of cycles revised exclusively for validation on unseen cycles. And 5, the outcome, this method guarantees model validation, reflects true generalization to new cycles. So the second ensemble models for accurate state prediction was as follows. It integrates diverse regressors with elastic net meta model and optimized hyperparameters for robust generalization. So we had base regressors, 6 heterogeneous models including random forest, gradient boosting, extra trees, k nearest neighbor, support vector regressor, and multi-layer perceptron. Perceptron provide versatile predictions that capture multiple data patterns. Hyperparameter optimization was performed by employing grid search cross-validation with group k-fold cross-validation, ensures robust tuning, prevention data leakage, and promoting reliable model generalization across group data split. And the program implementation was performed in Python. Elastic net meta model combines base regressors predictions by balancing L1 and L2 regularization, enhancing prediction accuracy through penalized linear aggregation. So regression matrix confirm model accuracy. The prediction errors were as follows. You can see on the graph for 3 test frequencies 0.5, 1, and 5. As you can see, the coefficient of determination is quite high here in each case, and absolute error is less than 1.25% in all cases. So model generalization on extrapolated cycles, high accuracy sustained up to cycle 300. So model was tested on unseen cycles 251 and 300. Validates robustness as prediction are squared consistently above 0.97. Slightly increased prediction errors at cycle 300 indicate accumulation of fatigue and microstructural degradation effect. Results highlight the model's ability to track evolving SMA properties under extended cyclic loading. Support practical durability assessment by capturing fatigue-induced shifts in strain behavior beyond training data. So on this graph, you can see hysteresis loop comparison for 251 cycle frequency 0.5 Hz. As you see, the results are quite good. And here you can see the prediction of hysteresis loop for cycle number 300. The results are quite good though, because the model have seen the cycles up to 200, but it's acceptable, I suppose. So also we have employed explainable AI with Sharp, interpreting strain prediction. So Sharply reveals both global feature impact and local prediction drivers in SMA hysteresis modeling. Sharply analysis quantifies feature contributions to model decision, enabling transparent interpretability. Stress is the key factor impacting strain prediction, outweighing other variables. Loading direction up-down has moderate influence, shaping model output contextually. Local sharp values reveal how combination of stress, cycle numbers, and loading phase drive individual strain prediction. This insight enhances trust and physical interpretability of the ML model in describing SMA hysteresis behavior. So on this slide, you can see global and local sharp analysis. So you see here that stress is the key dominant feature for this data, and also you can see that it also has the largest potential. And finally, I would like to conclude. To move to conclusions, model insights reflects physical principles of mathematic austenitic transformation and local dependent strain behavior. Increasing importance of the cyclic feature indicates microstructural changes in SMA during later loading stages. Models identifies stress as a primary driver of strain consistent with the SMA phase transformation physics. Loading direction manipulates the hysteresis loop shape, reflecting directional effects on the tensitic or stenotic transition. Alignment of model interpretation with established physical theories confirms both high accuracy and physical realism. Thank you for your attention.